So before we begin, I want to remind you what exactly we went over the last two lectures. First of all, we discussed the dual bounds, and then we discussed how to formulate the mathematical programming problems for computers to solve. Any questions regarding that previous material? So our dual bounds, I will just remind you quickly that we are aiming to bound the value of the objective function from the same direction from which we are into which we are trying to optimize. Into like we are basically, if we are talking about minimization, it's a bound from below. If we're talking about maximization, it's about bound from above. From now on, for the next lecture at least, we are talking about primal bounds, which is the other way around. For minimizations, it's the bound from above, and for maximizations, the bound from below. It is kind of non-trivial how to construct primal bounds. For dual bounds, we had relaxations, and we had a method to basically optimize in the space of relaxations, which led us to duality theory. For primal bounds, it's not as easy to construct a primal bound, because the only way to obtain a primal bound is to find a feasible point in the set we are trying to optimize over. So it is in fact it's not a trivial problem mathematically. Essentially, feasibility problem is equivalent in terms of computational complexity to the optimization problem. So essentially, what we are trying to do is we are trying to solve a problem in order to start solving the problem, which is kind of contradictory. But we have found several approaches to how to manage with constructing primal bounds. We will discuss them today. In particular, we will be focusing on heuristics, formulating the heuristics, the ideas behind them. Obviously, since they are heuristics, we are not proving them here. But in the following lectures, we will take a look at the problems where we can actually prove the exactness of the heuristics. So, any questions before we start? We see some more people here. Any questions regarding any material? No? Okay, that's great. So the first approach towards finding a primal bound is by following restrictions. A restriction, similarly to relaxation, it is also an optimization problem. Having a problem of maximization of objective function f dash over a set x dash, we say, so having a problem of optimizing f over the set x, we are saying that the problem of optimizing f dash over set x dash is a restriction of the original problem if x dash is a subset of x and f dash is less than or equal than f for all feasible x. It is in a way the reverse notion to the notion of relaxation, because for relaxation we had that x should belong to x dash, so it was the other way around, and the inequality was also the other way around. The obvious proposition that holds for restrictions is that the optimal solution for the restriction is less than or equal than the optimal solution for the original problem. I just want to remind you that for relaxations, this inequality was the other way around. So essentially, we can think of restriction as of a counterpart to a relaxation. However, if relaxations were commonly easy to solve, for example, LP relaxation was an easy problem, restriction is in fact often not too easy to solve. However, sometimes it is slightly simpler. We can take an example of a restriction here. Let's say that we are trying to maximize an objective function, a linear objective function, with the objective given with two vectors b and c over the two vectors of variables x and y, subject to the inequality that y is less than or equal than ax, and y is in fact is a real vector, and x is a binary vector, probably subject to some constraints, additional constraints that do not include y. A restriction would be, for example, to restrict this inequality to become an equality, just like that, and then substitute the y, the vector y, into the objective function in order to obtain a new restricted problem that is obviously a restriction of the original one, just because our new set x dash is in fact a subset of the original feasible region. This problem potentially has less variables, and therefore could be easier to solve, and would provide us with a feasible point for the original problem. Any questions here? Yep. The restriction of a relaxation. Yes, it's yeah. Basically, you can view it this way too. In fact, Z is a relaxation for the problem of finding ZRE, which is a good observation. So therefore, I'm saying yeah, it's a kind of a dual thing to relaxation. Any other questions here? Okay, good. So other than restrictions, we have so like even though restrictions sometimes are helpful, mostly people are focusing on other approaches such as heuristics when solving an IP, like finding a feasible solution for an IP problem. So one of the possible approaches, which we'll further discuss in a bigger kind of over a bigger umbrella, is the idea of rounding. So when you're formulating a relaxation, in this case it could be an LP relaxation, you are finding a point that solves this relaxation, for example this one, and round the solution. So basically you project the solution onto the set of integral vectors. After you have completed rounding, sometimes for example, if this was the solution, the result of rounding would be the same point, the 5,0 point, and therefore you would completely solve the original MIP problem. However, for this problem in particular, if we found this the optimal solution over here, the result of rounding would be this point, 2,5, and which is not a feasible solution, obviously. Therefore, rounding is just a heuristic. It wouldn't give us a feasible point necessarily. However, people have improved this heuristic, and we will discuss this further through iterative approaches, through iterative algorithms. Another heuristic that is pretty common and very low level is the greedy search. It's normally defined for a special class of problems that can be written in this form. You're minimizing, so it's a combinatorial problem. First of all, you're minimizing over the set of subsets of a particular objective function. Here it's written with C of S, such that V of S, a certain like feasibility function, is greater than the equivalent K, some number. Here V, K, and C are giving us with the problem. A greedy heuristic would consist in a scheme of finding finding components of the vector of the solution and basically assign values to it. Let's see what exactly, like how exactly we can interpret this argument here. So this minimization problem is being done over the set M, the underlying set that we are optimizing over. So basically, we are having some set M that consists of objects from 1 to n, and we are picking one element out of this set, for example, like J star, such that the following objective function is minimized. What this objective function is saying is that the cost or the cost of the set without the current set, the cost of the current set without the cost of the current set with the element J minus the cost of the set without this element J, divided by the feasibility, the value of the feasibility function of the current set with the element J minus the feasibility function of the set without this element J. Its relationship must be as small as possible. So you can think about it as this addition is basically it's how much cost does inclusion of this element J, how much cost reduction it gives to us over how much infeasibility this like addition of this element J would be suffer. So we are essentially trying to find a J to which the additional cost, the relationship between the additional cost and the excessive infeasibility would be the smallest. Let me actually switch for now for the particular example of binary knapsack, just to illustrate the idea, and then we will come back to discuss it in more generality. So we are having this problem. So we are here optimizing over the set of 7 objects. Here we have a string X, a binary string that encodes all of the possible subsets of 7 objects. And we are maximizing the value of the subset subject to a capacity constraint, so certain capacity constraint that we have to obey. Basically, what this this value Cj over Aj will tell us is that we are basically this is how much. So if we interpret this numbers as weight of an object, then the Cj over Aj would be the amount of value per kilogram or per pound that we are gaining out of picking up an object J, right? Is that clear? Any questions here about that? Okay, cool. So we are when we are ordering, we are trying to go from the highest to the lowest. So we would like to gain as much as possible from a pound of an object. Therefore, we are ordering our set of 7 objects by decreasing of this number. And then what we are doing next is that we are picking objects one by one in case they still fit into our into our backpack, in case we still can carry them. So following the greedy scheme, we take x equal to x1 equal to 1. So we are picking up the first object just because it fits in. We are picking up the second object because it also fits in, because 4 plus 3 is less than or equal than 9. It's 7, and we have to skip the objects 3, 4, and 5 because they cannot fit, even like if we add 7 or 5 or 3 to our back, like basically they introduce too much invisibility into the problem. This object they cannot fit in. Therefore, we are picking up the object number 6 and skip the object number 7 because our backpack is already full on full capacity. Therefore, the result of the greedy approach in this case would be this vector with value 22. Now, more generally, what we just did, like when we were ordering, we basically were picking objects. So our S was the set of, our set S, the value, the subset S was the set of objects from 1 to, let's say, J, that we have already went through. So after we have ordered them, we have obtained like our, like basically when we are at set J, for example, here, when we are considering picking up object number 3, our set S is the first 2 objects, right? And we have the object 3 that is outside of set S. And when we are finding that argmin, we are essentially trying to understand which object should we be considering next. So in this case, we have already ordered our set. Therefore, we are picking up the object number 3 into consideration. And the step number 2 over here is telling us if we are including our object number 3 into set S or not. So if V after the function V, after we have included the object J into backpack, if the feasibility still holds, then it is safe to include, and then we do include the object J. If we did not, if we were not able to fit the object J into the backpack, then we just throw it out and never think about it again. This is basically the formal form of defining a greedy heuristic for arbitrary functions C and V. It's important to say that it's not necessary that they are linear. So it is quite a general approach. Any questions regarding the general form and the example we just went over, the greedy approach? So good. Cool. Yeah. So this specific approach, in case we are talking about IP, if we're not talking about combinatorial problem, but we're instead talking about IP, we can formulate the same strategy of a greedy heuristic by ordering the objective coefficients from the biggest to the smallest, and then picking setting the value xi according to the difference between the value functions, the invisibility functions f of s. So this is another kind of extension of the greedy heuristic for the case when we are talking about IP problem specifically. Any questions regarding the reformulation for IP? No questions? Okay. All right. So the next heuristic, the next kind of conceptual approach is the local search. Local search, in a way, is a kind of like direct extension of the greedy heuristic, because it kind of expands the notion of locality from the greedy heuristic. However, it is also a very important extension to the local search that is commonly used in continuous optimization. It's like where we normally use the notion of like the notion of locality provided to us by the topology of the space over which we're optimizing. In the IP case or mixed integer programming case, we are relying on our own definition of locality because the topology there is not really well defined. So again, talking about a combinatorial problem, we are talking about the minimization of an objective C subject to an indefeasibility function G, but this time we're going to be talking about the equality constraint. So the indefeasibility function needs to be the indefeasibility function of S of the set needs to be equal to 0. We're gonna assume it without loss of generality because you can just define your function G to be the indicator function of some like system of inequality or something. So the local neighborhood needs to be defined in advance. So we are saying that, let's say that we are optimizing over a grid here. Let's say that our sets F are in fact subsets of the points in the grid, and we are trying to pick the best a subset of points on the grid, such that the function C of this subset is being minimized. We would need to define a local neighborhood of a subset of points. For example, if we have a subset that consists of 3 points, this one, and let's say this one, we can define that, well, a local neighborhood would be any subset on the grid such that it differs from this subset in 1 point. So basically, a subset of this form would be a local neighborhood because we only switched from this point to this one, or the subset of this form would also be like another example. We again switched from this point to this point. So this generally depends on the definition of what a local neighborhood of a subset is. But for now we're gonna be keeping this abstract and saying that we are able to define a local neighborhood, and we will see into like closer to the examples what exactly the neighborhoods would be in our case. We also formulate the goal function that is given to us by the scalar alpha, that is defining to us how important for us to actually satisfy the system of equations that we have in the feasibility constraint. Like if you really care about finding a feasible point, it would be wise to set this alpha to be a very large scalar function. But if you would like to find, like if you have found a feasible point and you would like to improve it, for example, you can decrease this alpha so that your solution is still a feasible point, but a better one because you're taking care of the objective function in the goal that you're trying to optimize. Any questions regarding the setup that we are operating in?
Can you explain once more the QMS set?
Yeah. So let's say that so this is something that we are given by the problem. Let's take a look at the example. Actually, take a look at the example. Let's say that we are managing a communication network represented with a graph, like a specific graph. That needs security improvements. n nodes. Our adversary can put a number of communication lines out of service, and the greatest damage is done to if our network is being split into two equal unconnected parts. How can we know where to build new lines to prevent that? So let's say that we are having a network. I think I probably have it. Yeah, we are having a network like this. 1, 2, 3, 4, 5, 6, let's say cities, and they have like landlines of this topology. Right. So we are having like a topology of landlines like this, and our adversary can take out some lines, and we would like to prevent it to like if it took out lines and there is like the large part of the network is still operational, and like there's like small little island that is being isolated. This is not as bad as if I just disconnected the network, parted it into two parts by removing certain edges. I would like to understand where should I build new landlines so that I prevent that from happening. How can so we introduced the cut set. The cut set delta of SV without S is the set of edges such that the beginning of the edge is inside the set S, and the end of the S is outside of set S. So we are basically saying that if we are given a set of nodes, for example, 1, 2, and 6, then the cut set is a set of edges that have one end inside the set S and another end outside of the set S. For example, for 1, 2, 6, this edge would be inside our cut set. This edge would be inside the cut set. This edge would be inside the cut set. This edge would be inside the cut set, but this one would not, and this one from 2 to 6 would not. Okay. So this is what cut set is, and what we are really asking is what is the minimal size of a cut set. So what is the minimal size of the cut set so that our the size of the set of vertices is based on is exactly n over 2. So if we are talking about six bases, 6 cities, then it's exactly 3. We would like to know what is the way to split this into 2 so that as few landlines are being damaged as possible. And then we will know that we will need to build new landlines between S and VLS. So we will solve the problem. Let's take a look at how to try to approach this. So we are trying to minimize over the set of vertices this function, this cut set, the size of the cut set. We're defining the neighborhood. The neighborhood in our case is going to be Q of S. So for each set of vertices, for each set, for example, 1, 2, 6, we are saying that the Q of S is going to be a set of subsets of vertices such that the symmetrical difference between, or like the difference between the T and the original set S is equal to 1. For example, if our set as 0 is 1, 2, 3, 1, 2, 3, then so let me write it down because we need more examples. So let's say that our set as 0 is 1, 2, 3. What is the Q of S0? The Q of S0 is it's going to be 1, 2, 4, 1, 2, 5, 1, 2, 6. It's going to be 1, 3, 6. It's gonna be 1, 3, 5, 1, 3, 4, and three more subsets. Does that make any sense? Should I continue? Okay, let me continue. 2, 3, 4, 2, 3, 5, and 2, 3, 6. All of these subsets of nodes would belong to the set of all of these subsets. All of these subsets that I have written down would be neighbors, local neighbors of the set S0, because all of them differ from S0 in one. Yes. Yeah.
Yeah, makes sense. Yeah.
Cool. Okay, we'll come back to this when we understand what exactly we are doing here. The heuristic of local search. So the local search heuristic is a scheme where we are taking a set F and we are finding a minimizer of the goal function F over this local neighborhood defined by the set S. So what it means in this case, in this example, is that given that we are we start with the set F, we are looking among this 9 subsets, not among this 9 candidates, the best one. So we basically evaluate the function F at each of these points and see where which point would give us minimum. And if this minimum is actually smaller than the value at S0, we would just switch from S0 to one of these subsets, and then we will continue and we will iterate this procedure more again and again. Question? Yeah.
So is this
It's guaranteed to converge somewhere. So eventually, what it converges to is called a local optimum, which is defined when you define a local neighborhood. So a local optimum obviously is a point. Okay, so it's guaranteed to converge, of course, after certain assumptions. So, for example, if you have a finite system of sets, then at some point you will, at most after trying all the possible options, you will converge somewhere from which you are not you're not able to progress anywhere. But it's not guaranteed to converge in polynomial time in general. However, we will take a look when it is in fact true that you are guaranteed to converge in polynomial time, and sometimes you're guaranteed to converge in polynomial time to the global optimum. So that's basically what we are trying to achieve here. So any questions regarding what is local optimum? Because I don't think I ever defined it. Is that something that needs to be defined? What do you think? No? Okay. Any questions? Come on, guys. Okay. Okay. So let's take a look. Let's come back to this to the example once again. So this is the set that I have written down. This is the Q of S0. And here I have written down the costs for each of this subsets. You can see that the smallest cost here is in fact the cost of 2 for the subset 2, 3, 5. So we are picking the subset 2, 3, 5 with cost 2, and we are taking a look at Q of S1 of this new set 2, 3, 5. it turns out that in fact in Q of S1, I don't want to write it down once again, but if you were to write it down, you will realize that this list of costs will consist of numbers that are all higher than 2. So this S1 is in fact a local solution for this particular problem, and moreover, it's a global solution to the best of my knowledge. So it is impossible to it's possible to split this graph into 2 parts by by removing just simply two edges, and these 2 parts are going to be equal, and so you need more landlines between these parts.
The cost was just the number of edges going in between
the two sets. Yeah, that's right. Okay, any questions here? Okay. Let me actually come back, since you are asking questions sometimes. Probably there are any questions regarding greedy heuristic, because I feel like there could be questions. No? Okay. All right. So there was a question about convergence. Very good one. We are in fact, when we are doing local search heuristic, we are guaranteed to converge to a locally optimal solution. However, it's not really what we would absolutely love to do. We would like to find a global solution, and for that, one of the possible ideas to pursue is to continue search for globally optimal solution and forbid to come back. So basically, you are forcing, once you have, so you can think about it as follows. Let's say that we have some complicated landscape like this, and when we are doing local search, we're essentially we are picking a point. So this is our domain X, and like a single point on this domain is a set S, right? And we are taking a set S, then we are picking a locality Q of S, some local neighborhood, and we are optimizing over this local neighborhood, and we are finding a local minimum. Like we are finding the smallest point in this locality, and then we reiterate. We build a new neighborhood, and we re-optimize it. And at some point, we do converge to a local minimum, from which it's really hard to escape. However, if we agree that we will not stay there, we would possibly just say that we will forbid to come back to this point, and we will force okay, so if you are finding the same point once again, just find the next best point. So do not do local the exact minimization, but do the minimization over all of the points except for the ones that you have been to. In this case, since let's say that we are over a discrete set, we're gonna be able to. So if staying at this point in particular, we would not be able to come back this way to following the path that we have taken before. We would continue moving upwards until we have reached some location from which we can already go down without going back. So if we go up long enough, at some point we might switch to a separate valley that will bring us to a point with an even better objective value than we have had before. And this idea will appear once again later today during the lecture. But one of the ways to implement this idea in local search is called the taboo search. When we are maintaining a first in, first out list of sets S that we are gonna be ignoring when we are choosing the next step, the next point to consider, and we will update this list every step we are we are taking. Obviously, if your list consists of just 2 sets, it's probably not enough. It's been studied that like there's a magic number like 7 that gives you a very good bound on the size of the list that you need to maintain in order to converge a good to a good solution. It's just engineering wisdom. So if we are forbidding to stop, then when do we say that we have converged, right? It's not clear at all. The idea is that we just set up the number of steps in advance through which we agree that we will strive through, but after we have completed these T steps, we will pick the best point with the best objective value that we have encountered so far. So we will stop after exactly T iterations without improvement. So like if we have made like T steps and there is nothing better than we have found already, we will just terminate our algorithm, say that what we have found is good enough. Sounds good? Okay, so the next idea towards the next development towards finding the global optimum, or another way to actually escape local minima, is by following simulated annealing. An idea from physics, actually, where we are still talking about the same combinatorial optimization problem, but instead of defining just the local neighborhood, we are defining a probability distribution for like over this local neighborhood. So for each set S, we define a local neighborhood and a probability distribution over this neighborhood for a reason that we will discuss further. So we have a goal function, which is exactly the same that we have been discussing in local search, and the simulated annealing goes as follows. We are picking S dash on random from the distribution that we have assumed existing. We are taking we are considering the difference between the objective, the value of the goal function on the new point S dash, and its difference from the value of the goal function on the previous solution S. And if our new solution is in fact better than the previous one, we just switch. We just do the thing that we have considered during the local search method. However, if we have found like if our new S dash is worse than the previous point, then we will transit to this new point S dash only with certain probability that will depend on the gap between the two solutions. And this probability is called the Boltzmann law, and it's gonna be reduced as far as we go along along our procedure. So with every step, we're gonna be reducing. So like given a certain particular value of the gap, the further over the procedure we go, the smaller is the probability that we will take the step towards the new point with the value of this gap, with this particular gap. Any questions regarding this simulated annealing? Yep. Precisely. Yeah. So this is instead. So before we had the parameter T, which is like the number of steps that you can go without improving. Now instead of T, you have L1 and L2, which are basically for you to set, because it's not quite clear. So it's up to you to understand how how great are your leaps when you need to actually reduce this probability, when you need to stop. That's yeah, but that's a good question. There are specific like suggested values, like default parameters for L1 and L2. But you're essentially free for yourself to pick depending on the specific applications that you have in mind. Yep.
Check my understanding. So we're basically saying, so you are not reducing the goal function. You still might want to move to that set anyways with that quality in order to see if there's a better solution.
Absolutely, yes. So that's exactly what's happening. Anyone knows why it's called annealing?
Isn't it for like the metals and you would like with the breakdown of carbon?
Exactly, yes. So you can think about it as basically hitting the system up. So basically you are when you are in so this T parameter is in fact the analog of temperature in a physical system, for example, in a metal. So when we are at a high temperature, and like so the annealing idea is coming from minimizing of the like potential energy of a body, right? If you have a potential energy that is like normally it's very complicated, the annealing is the method to reduce its energy to make it more like flexible or give it the parameters, the physical parameters that we want. And when the temperature is high, your system is oriented in areas with high levels of energy. So it's basically it's gonna be situated somewhere on the top, and it will eventually concentrate its presence in local values, in local valleys, so-called valleys. And the bigger the deeper the valley is, the deeper the better the local solution is, the better is the probability that you will eventually fall into this valley. And basically people from optimization decided that they want to take this conventional wisdom from material science and try to apply it. Okay, sounds good. The next chapter here is the next heuristic is the genetic algorithm, which is also a very interesting heuristic with plenty of different hyperparameters, plenty of choice, of freedom of choice. Also, it's kind of giving you freedom to, I know, play God for people who like to do that. So you are again considered the same combinatorial problem, and you do not probably define a locality for each subset, but you are defining the goal function, and you are normally considering 5 different operations that you can do with the set. So you're operating with a population of some subsets S. So the population here is denoted with a calligraphic F. And you're given some, like, let's say a finite sets, like finite set of sets, which is your population. Now, what you can do with the population? First of all, you can evaluate it. You can just find the values of the goal function on each of the members of your population. You can do a parent selection. You can find pairs of, like, when I say find pairs, it's theoretically an arbitrary procedure, and it doesn't really have to be pairs. But like mostly it's considered to be with pairs. Like according to some rules. So you're pairing up members according to some rule. Then there is a crossover procedure that, given the for example, the two parents or whatever the number of parents you are operating with, you're producing offsprings. You're producing some other subsets from the set N that would that you would think of as better solution, but potentially better solutions. And also all of the members of the population are potentially can be mutated. So basically it's some random, most likely it's a random modification of a member of a population for it to become a different member. Eventually, normally you proceed with crossover and mutation several times within a genetic algorithm step, and then you are doing another evaluation and population selection when you are based on fitness, based on the value of the goal function. You are picking another subpopulation that will go into another round of this genetic algorithm. Any question regarding the overall procedure before we dive deeper into what exactly is the example? No? Okay. So the implementation of the parent selection is normally quite straightforward and simple. The intuition is that you would like to choose better solutions with high probability. So if you have evaluated your members, then you know the values f of s and f of t, and you can choose the members of the population with probability that is proportional to the fitness. Doesn't have to be. It could also be like something like Boltzmann law, like the one that we have just seen. But it's a common choice. The implementation of crossover is even more variable. So we can a couple of important examples are the 1-point crossover, 2-point crossover, and uniform crossover. Just because it's something that we commonly observe in biological systems. So given two members S and S dash, we can represent them as binary strings, obviously. The X string and the Y string. It doesn't have to be binary, but it's easier to think about them as binary. And the 1-point crossover at a particular position P results in two children. One is the string X with the position P plus 1 being swapped with the string Y, and the string Y with the position P plus 1 being swapped with the string X. Similarly, you can define 2-point crossover. Obviously, it just means that you swap two values in the first string with the two values in the second string, and obviously it can be extended to whatever number of points that you might think about. But it's more common to use 1 or 2-point crossover, because the further you go, the more complicated it becomes. It's harder and harder to prove anything about it. The uniform crossover results in just a single offspring that is a random combination of the entries of the two binary strings, X and Y. Any question here? Okay. So the implementation of mutation is normally essentially you are picking on random several points in which you would flip the bit that is standing on the particular positions in the string representation of the number S. Let's take a look at an example of application of this genetic algorithm, and something that is not directly related. So it is obviously an integer programming problem, but how can we look at this problem at a different angle, that will allow us to simplify the application of genetic algorithm. So we have this generalized assignment problem where you have m jobs and n workers, and a worker can only perform a single job, but a job can be performed by multiple workers. So it essentially means that there are multiple like tables on which workers can work, and they can, like, a job is basically a production of a specific type of item of a product, and a single worker can only work on one type of product, but like several workers can produce the same type. We have a capacity, so let's say that there's a machinery that limits our production, and a worker I takes ij of job j capacity, and the total capacity of job j is denoted with bj, and a worker I contributes cij to the total profit if he works on the job j. What is the optimal assignment? This is the problem that is the mathematical representation of this question, where we have this inequality over here instead of our normal inequality in the assignment problem, where we have the summation over I of xij equal to 1, if you remember that.
Excuse me?
Yep.
So the cost here is the contribution to the total profit, right?
Right.
And then we want to minimize it.
Yeah, so it's probably not a contribution to the total profit, but I know, a loss that you can incur. Or you can just say that it's maximization, or you can say that the Cij are in fact negative. But yeah, I need to fix this. Thanks for letting me know. Yeah, so we are dealing with this problem here, and it's obviously a binary optimization problem, like a linear problem. However, it turns out that it's easier to think about it as the following. So our single solution, or the member in the population S, can be represented with this matrix X, but it also can be represented as an integral vector, or the integral string consisting of integer values from j1 to jm, where ji is the job of a worker I. You probably remember we were considering a problem of this form on our first lecture. The objective here, C of S, is going to be summation over I of Ci ji. Probably remember my comment that it's not a linear program anymore, right? It's not a linear objective, but the benefit of this kind of heuristic is that we never really said that that C or G has to be linear functions. So we can tolerate that totally. The infeasibility function is also can be defined in this case as the summation over j over the jobs, the summation of aij's such that like, so this the summation over it's actually summation over I over of such i's, so that it's summation over the set of workers, so that the worker I is performing the job j. So the summation over i's of aij minus bj, and this plus here means that we are taking the positive part, which is the maximum over 0 and x. So the x plus the x superscript plus is the maximum between 0 and x. You probably heard about this before. It's called also the rectified linear unit or value function. So the 2-point crossover and 2-point mutation would lead to solutions that are satisfying this constraint, the equality, and the integrality constraint. So no matter what we do, essentially, with this string, in terms of mutation or two-point mutation or two-point crossover, we will only need to worry about this C and this G, which really does put us into the overall framework of genetic algorithm, and therefore we can just take this expressions here and throw them into the machinery of genetic algorithms, see what it does to us. So we don't really need to encode this inequalities, this constraints anymore, just because of our clever choice of the strings with which we will represent our members. Any questions about this example? No questions? No questions, guys? Okay. All right, so let's take a look at, so what we have covered so far were mainly the heuristics that you can personally utilize when you are attacking a new problem. Like local search method, it's a very general approach that requires a lot of hyperparameter setting, hyperparameter instituting. You can put a lot of your own understanding and your own like practical knowledge about the problem when you are designing an algorithm of that form. So it's just an algorithm scheme for real. So all of the above were mostly focusing on the algorithms that are useful to you as a researcher when you're trying to solve a problem. However, there are heuristics that are immediately utilized by the solvers when they are trying to come up with a primal bound for a problem that they are solving. Right now, we're gonna be discussing more like on their account. They are different because they probably not as capable of incorporating prior knowledge about the problem or like your like understanding about the physics of the problem, but they are very extremely algorithmic and simple, and then they can be repeated quickly. Therefore, they're mostly used in the tools, the computational tools that are encoded with the MIP solvers. So the first heuristic here is the rounding heuristic, which we have considered before. You're essentially projecting onto the set of integer values. The other heuristic is the heuristic of a shift, when you are picking a single component of a vector, and you're basically you're shifting it by a predetermined amount that decreases in feasibility, which means that, for example, if you have an feasibility function of the form of this form with a v, like this one, and you have it like way too high. You have v of s much larger than k, and you know that if you decrease a particular value of xj by a certain amount, that will decrease the value of v of s, then you can just do it. You can just try to perform the shift that will decrease the invisibility. There's a very important idea of fixation, or fixing the components. You can set xj to some value that is integral, for example, using preprocessing or constraint programming to tighten bounds due to the fixing. So before you have started solving the IP problem, you can say that I know that I want xj to be equal to a particular number, for example, to xj to be equal to 1, and you can incorporate that into your program either by just substituting it directly into the programming, your formulation itself, or by adding constraints into the programming problem that you have have created. So another approach is to solve a linear program with variables that have been fixed and run the solution. So it's essentially the idea of fixing can be extended to solution of relaxations. For example, you know that a particular component must be equal to a particular number, or you expect it to be equal to that number, and then you solve a relaxation instead of solving an IP. That might result in resolution of a faster resolution of the problem, a faster obtaining and approximating the value of the optimal objective value with a greater speed. If you are understanding after performing the previous steps several times, you can potentially include more fixed values into the problem and proceed with mixed and integer programming problems solution for smaller problems. So basically, it's fixing is a way to reduce the size of the problem too. An extremely important tool. Let us look into more examples of how this construction heuristics work. The first example is the dive and fix. Let's say that we are so what I will be discussing here, mostly focusing on integer programming or binary programming problem, but it's very easy to extend this formulation to mixed integer programming problems. I will not stop on that, but I assume that it's obvious to you. If it's not, please let me know. Given a solution to the LP relaxation, XLP, to a binary problem, we are finding a non-integral variable that is that has the closest value to an integer value. So basically, we are finding j such that xj is not integer value, but the minimum. So but it is in fact very close to being an integer, either 0 or 1. For example, a value of 0.001 is very close to being 0, and the value 0.99 is very close to being 1. So it's very likely that rounding those particular values would bring us more benefit and will result in a closer solution to the one that we are trying to achieve. So we are rounding this particular variable that is closest to being integral, and by adding the rounding constraint to our optimization problem, and then we resolve the LP with basically with the one less variable, and we can proceed with this until we run out of variables or until we have an infeasible LP. If we have obtained an infeasible LP, that means that our heuristic has failed. We need to find something else. And if we have run out of variables, that means that we have fixed all of the points, and potentially we have found an integral point that is feasible to our problem. Any questions regarding the idea of dive fix? I have a question to you then. Which variable would we fix in this situation when we have found the solution here? We have found this solution. Which variable are we going to be fixing next? This is our LP. Yep. Second variable. Okay, so it will become what? It will become x2 is equal to 5. Okay. So we now we're gonna be optimizing over this subset, right? And what's gonna be the result of it? The next LP. What's gonna be its optimal solution? The next LP in the series world. It will be infeasible essentially, yeah, because our our set x2 is equal to 5 like does not intersect the original set that we are optimizing over. Therefore, our heuristic here would not work. This was the precise example when rounding doesn't work. Okay. Any questions here? No questions. Okay. The next approach and the next kind of idea here is the neighborhood rounding. When you are given an IP problem in this form and a solution to an LP relaxation, you can solve. You can essentially bound. You can add bounds to bound the particular components of the vector x by the rounded the floored and the sealed values of the component of the XLP, and resolve the new IP, hoping that it will give you better like more integral solution, like a solution with a bigger number of integral components. That's what I'm saying for real. So essentially, this is a procedure that you also can do iteratively. After you have found a solution to this problem, if it's feasible, then you can take this new problem as you can kind of keep adding new constraints until the problem becomes infeasible, or you have found an integral solution. In case of this example right here, we would likely change our problem by adding two new constraints, which would be putting us into the box over here, and also also over here. So now we would optimize over the intersection of this square and this triangle. So now we would probably find a point that is different. It's actually unlikely. It's still going to be the same point, but if our object, like it essentially would depend if we are it would depend on what exactly we are trying to. We might actually also modify our objective function. We'll talk about this a bit later. So okay. Any question about neighborhood rounding when we are finding rounding in a neighborhood? Okay. The next heuristic is a feasibility pump. It's a more kind of complex heuristic where we have again we are talking about IP, and we have an LP relaxation solution. We can iterate the two stages. On the first stage, we are projecting X onto the space of integral vectors. So we are rounding, and then we are projecting it onto the initial the original polyhedron, or the original formulation of the IP that we were working on. As an additional step, a very important one, there is an option to add a cutting plane, so that it restricts us from being projected onto the same point several times. However, in this particular feasibility pump statement, we are just basically, if we started to cycle, if we realized that after these two iterations in a row we ended up staying in the same point, then we can assume that our heuristic has failed, and we need to start doing something better. The attractive thing about this idea is that this projection can be done quite easily. It can be done very efficiently just through a solution of a linear programming problem. And another improvement over this heuristic is to do projection on this step, not of a single point, a specific single point, but of an entire ray that goes through an interior point to the projected solution here. So let me actually give you an example of this. So for example, we have like that. We have an optimum solution somewhere here, and we have our first step of rounding has given us. So this is our XLP. Our solution of rounding has given us some other integral solution x hat, let's say. What we do next is assuming that we have some other point that is in fact like internal for at least for the relaxation. We can put in an entire line, and then what we can do is we can find all of the integral points that are close to this entire line, and then project those points onto the polyhedron P. For example, in this case, let's say that our integral points here are here, and this gives us the network, the grid, and our closest integral points would be, for example, this one, or probably on this particular picture it would be this one. So after we have found an integral point that is closest to the line, which is easier to do because it's just a one-dimensional projection onto a one-dimensional space, we can try to project it onto the polyhedron P, and we might get a better result than just projecting this point onto the polyhedron P. For example, this is a trick that could help us with the initial example of this form. So here we could use a point, for example, 0, that would definitely be inside of the feasible set, the initial feasible set that we are talking about, and draw a line of this form, and then try to project integral points onto the line, and then reuse the projection onto the polyhedron. Okay, so this is an approach that is called the feasibility pump, and it's arguably the most common method for algorithmic finding of feasible points. Any questions regarding feasibility pump? Okay. Yep.
The line, how do you decide like from how do you decide line? Is it like
like which line we are picking?
How do you decide where the line goes like?
Yeah, so I'm assuming that there is a prior knowledge about a point x0 that, let's say, belongs to the interior of the set that I'm optimizing over.
To just find that.
So it doesn't have to be feasible, because if you have a feasible point, then you probably don't really need that feasibility pump, because that feasibility pump is trying to find your feasible solution. But it must lie in the interior of, for example, the LP relaxation. Finding a point that lies in the interior of the LP relaxation is much easier than for finding a feasible solution. That's good. Okay. Any other question? All right. So the next important heuristic is the proximity search. So we are again we are talking about the IP problem, and we can try to find a feasible solution with an objective. Oh, okay. So now we are switching from a problem of finding a feasible solution to the problem of finding a better feasible solution. So from now on, we're gonna be assuming that we already have some feasible solution at hand, and now we would like to improve it. We would like to find something better than we already have. So let's say that we are given a feasible point X of an IP of this form, and we can try to find a feasible solution with an objective improved by delta by solving the following integer programming problem. We are minimizing over the potentially integral set of z, the vector z. Basically, we are minimizing an objective that consists of two terms that force z to be bind to the values of x. So basically, what we are saying is that the deviation of z from x should be minimal, right? So like this term measures deviation of z from 0 when xj is equal to 0. So this term basically measures the deviation of z from x at points where at components where xj is equal to 0, and this term here measures the deviation of z from x at the components when xj is equal to 1. And since we would like our objective to be improved by delta, now we are putting the objective into the constraints and saying that the optimal value of z must be greater than or equal than the optimal value of x plus some margin delta that we are setting up in advance. So we are not optimizing over delta. It's our constant. You can see that it's actually very common trick to swap between the objective and a constraint. So you could think about it as actually being like a part of the constraint, because you're trying to get as close as possible to x, but in this particular formulation, it makes much more sense to put it into objective, because you have no idea how close you really want to be, but you have an idea of how much better you want to be. So in this case, you're putting your objective function into a constraint, and you can see it commonly in different kind of reformulation or the supplementary problem formulations that are being resolved automatically by the mixed integer solvers while it's solving your original problem. Any question about the proximity search? No question? Okay. So the next important heuristic is the relax and fix idea. Again, it's like if you have the fix in the name, that means that at some point you're going to be fixing a variable and then solving a problem with this variable being fixed. In this particular variant of this heuristic, we are splitting our set of variables into two. So our first set of variables is denoted with x1. Our second set of variables is denoted with x2. And this splits our objective function into two parts, c1, x1, c2, x2. And our constraints are also being split into two parts. A1, x1 plus A2, x2 is equal to b. We are assuming here that our problem is given to us with like in the standard form, where we have equality constraints, and the inequalities are all put into the form of non-negativity inequalities. You can see that you essentially you can basically you can do this to any problem, any integer programming problem, and similarly you can do with the mixed integer programming problem, and you are not really bound to any specific structure. Therefore, nothing really tells you how exactly to split this set of variables into two parts, and it's up to you to design a particular heuristic, particular algorithm. So there is a hidden hyperparameter placed here. So the first stage of the reluctant fit approach is to relax the second set of constraints. So instead of optimizing over like an integer set, we are optimizing over a set of real numbers, non-negative, a set of non-negative real numbers, which potentially makes our problem a lot easier, because the number of integer variables complicate, the bigger the number, the more complex the problem is. With a smaller number of integral constraints, integral variables, you might be able to get the solution x1, x2, x1 bar, x2 bar, and its value z bar, which is a solution to a relaxation. So we basically can think about that the z bar is in fact gonna be greater than the original solution z. So here we are on the first stage, we are gaining actually a dual bound on the solution of the original problem. What we do next is we are fixing all of the variables x1. So we are adding this constraint here that x1 is equal to x1 bar, the solution to the original problem, to the first stage, to the relaxation, and we are solving for x2 now being integral. So we are forcing x2 to be integral when we have forced x1 to be fixed. So we are taking so this value of this new problem is going to be called underline z, and underline z, first of all, it must be smaller than the value of z, just because if there is a solution to this problem, then all of the variables must be integral. X1 and x2 both must be integral, and all of our constraints must be satisfied. Therefore, z underlined must be smaller than z. So therefore, we have the solution to the second problem will give us the vector x bar x2 tilde that will give us the primal bound we were craving. It is important to note that there is no reason for us really to just consider separation of the variables into two parts. Moreover, we can consider a separation of this variables into like random separation into a various number of subsets. For example, like five stages of relaxant fix is a common thing to see in the applications. So this is a very powerful heuristic for you to utilize if you are looking for a feasible solution to a problem. Okay. Let me see if there is any comments regarding what we have done today. Any questions? We are actually about to finish with the primal bounds. I want to see if there are any questions here regarding the relaxant fix or any others. Yep.
What is the reason why you have to separate the constraints? Just because the variables are in groups as well?
So the reason for us to separate into two groups is that we are in fact unable to solve the integer programming problems with the huge number of variables we have initially. So in order to divide that number into by some number, by 2 or by 5, we need to separate it into several groups so that our problem becomes kind of visible. And so one thing that I didn't mention here, but along the way, we were considering that this objective is the same one that we have in the original problem, but it really doesn't. If you're just interested in finding a feasible solution, it makes more sense to try to vary the objective, just because, for example, if we are talking about this particular example, it's obvious that it's pretty hard. Like considering all of the heuristics that we have discussed so far, it's only the very complex or very involved one that would give us a solution, a feasible solution, starting with this solution of the LP. This solution of the LP is something that we are getting because we are using the same objective function that we had in the original problem. So if we were to vary the objective function, we would be able to stumble upon different points other than the one that is clearly very unlucky for us to deal with. Okay. Any other questions regarding primal bounds, or how's it going with the Groby Pi and the solution? Because I noticed that not too many people showed up to the previous discussion section. I was wondering if that goes because everything is clear, which is likely the thing. Is that the case? Pretty nice. Okay, that's cool. All right, so I will finish here. Thank you very much for your attention. I will stick around. Let me know if you have any questions.